Okay.
Okay.
Good day to one and all who are present here. This is Gerard Deepak, a senior research scholar from National Institute of Technology, Tiruchirappalli. I'm here to present the paper titled Ontology-Based Knowledge Description Model for Climate Change as a Domain of Choice. The co-authors of my paper are Mr. Deepak Surya and Dr. Santanavijan A from National Institute of Technology, Tiruchirappalli. So going to the abstract, so ontology modeling and visualization is quite a tedious and a challenging task, and it is of utmost importance for specifically for highly specialized domains like that of bioinformatics, chemical informatics, and climate change is also one of the domains which is of utmost importance, as climate change has a geological perspective as well as a social perspective. And most of these times, okay, there is no ontology for climate change with geological as well as socio-technical perspectives. So climate change will, could be a very small word, or it could be a very common word, but there are absolutely no proper ontologies which are available for climate change. Especially the technical and geological aspects are not at all considered in the existing ontologies. Why ontologies? So ontologies are nothing but they are a set of terms or vocabularies assembled as taxonomies with relations, reasonings. So ontologies are descriptor models, knowledge description models for knowledge representation and reasoning. Why represent knowledge and why reason knowledge? Okay, knowledge representation and reasoning is quite important so that automatic information systems can be built so that they would make decisions based on the ontology. The World Wide Web is crowded with information, and the present era is the era of the web of data. We have a lot of data, we have much information, but we don't have knowledge. Okay, the knowledge over the World Wide Web is quite sparse. So all this information has to be converted into knowledge. Okay, and learning algorithms like the traditional machine learning algorithms fail to do so. The reason is because training these ML algorithms from live data, specifically which is dynamic, is highly is highly a challenge. So as a result, why simply train and why simply do unnecessary training and reduce and increase the computational power? So it's better that we can have ontologies, okay, which would ready-made, which would by itself yield decisions, and the systems would be trained very easily. This paper presents an ontology for the climate change as the domain of choice, both from a geological perspective as well as a social technical perspective. It is developed upon extensive research on the domain. Knowledge is represented as classes associated with each other by a link. The ontology is visualized using Web BWL and converted, okay, and it is modeled using the Web ProTeach. The proposed climate ontology has been evaluated both quantitatively and qualitatively. A reuse ratio of 0.95 has been obtained. Yes, so we discussed why ontologies and why ontologies are required and how information systems can definitely make use of these concepts in order to arrive at decisions. For example, let's get into the fourth point here. The Earth's equilibrium temperature depends on the rate of a shortwave radiation emission and the gain of long wave radiation. Shortwave radiation is the energy radiations received from the sun by the Earth, while long wave radiations are radiations that are emitted out into space. The Earth receives the energy radiations emitted from the sun, and an equal amount of energy is emitted out by the Earth to maintain its temperature. However, gases in the atmosphere such as carbon dioxide, water vapor, and methane trap the Earth's radiation. So the amount of energy received is greater than the amount of energy emitted. So these 2 points which I read out at this moment is an extremely complex geology, consists of extremely complex geological phenomenon. Okay, and this kind of phenomenon cannot be easily deciphered by an information system. That is why ontologies have to be modeled. So such complex phenomenon have to be intelligently fed into the information system. For this, we require a well-structured conceptual ontology which describes the phenomenon. Motivation, yes, motivation, because There is absolutely very few ontology for specialized domains like bioinformatics, cheminformatics, etc. Climate change, though it seems very common, it is a specialized domain because a lot of complex phenomena are there which should be depicted as an ontology, and henceforth we have modeled this. And moreover, geological and socio-technical perspective has been considered. So socio-technical means it is socio-economical also comes into picture there, and socio-feasible perspectives are incorporated for the ontology. However, there is no need to depict the geological concepts of ontologies and establish knowledge models to enhance geoinformatics and climate change becoming a potential domain plausible by machines. Yes, there is a need to. Yeah. Contributions in this paper, an ontology is developed for climate change, as we discussed, both for socio-technical aspects as well as geological aspects. The ontology modeling yields 96 classes, 54 individuals, and relationships are used in this ontology are divided into and strong inclusion. The phenomenon climate, the complex phenomena in the climate change is analyzed and modeled into an ontology based on geological and socio-technical perspective, and a reuse ratio of 0.95 is achieved. From here, my co-author, Mr. Deepak Surya, will continue. Over to you, Mr. Deepak.
Yeah, thank you very much. So, hey everyone, I'm Deepak, and well, this figure here that represents the proposed ontology model. So this is actually the ontology that we have developed for the climate change, and this has been developed upon very careful analysis and research. Yeah, please, next slide. Next slide. All right, so visualization, right? So after modeling the ontology and after the conceptualization of the climate change, after conceptualizing the classes, the next step is, of course, visualization, and it is the process that follows the conceptualization of an ontology, and there are a lot of tools available to visualize any ontology, but we have used WebProdigy, and there are so many visualization tools that are used to represent the ontology by making use of some graphical elements. And visualization is a very useful method to observe the patterns in the ontology, because otherwise it would be very hard, right? Of course, to able to observe any latent patterns in an ontology, like we visualize it, so it becomes easy. It becomes a much easier task for us to understand and discover some patterns in it. And it also reduces the search for information. Like anything, if it is represented graphically, it becomes a lot easier when we are looking for particular information, right? Yeah. And also a large amount of information can be examined very quickly. Okay, there are many tools available to visualize the ontology, and here we have used WebWorld for the visualization. And yeah, the ontology is then converted to OWL format using WebProdigy. Next slide. Next slide. All right, so this figure here depicts the class hierarchy for ontology, class hierarchy of the ontology that we developed. That is the climate change. That's the ontology that we have developed for the climate change, right? So here we have the topmost parent class. I mean, the topmost class in the ontology is climate change, and it has four classes, like four subclasses, and they are cause, characteristics, consequences, and mitigation. And as you can see, the concept or the class cause, it has again two subclasses, like it has again two childs. One is the natural cause, another is the man-made cause. And for natural cause, there are again two divisions. There are two subclasses. The one is the volcanic eruption, other one is the asteroid impact. And for characteristics, there are three subclasses. One is global warming, another is precipitation over land, another is increase in greenhouse gas concentration. And for global warming, it is again ocean acidity and ocean temperature. Concepts, the cause, characteristics, consequences, and mitigation, they are at the same level, right? This is well illustrated in the figure, as you can see. And for consequences, there are two main subclasses, that is political and economical. It's like what are the consequences of climate change in a political, in looking it for like in a political perspective and an economical perspective. That's what it is. And there's another class, sorry, there are other two subdivisions for consequences, that is environment and lives and livelihood. And for environment, there are four subclasses. Those are water resources, melting of glaciers, natural calamities, biodiversity. And for and at last for mitigation, like there are three, that is demand reduction, geoengineering, and methane stabilization. Right, next slide. Next slide, please. All right, so this figure here that depicts the relationship between the objects. Yeah, next slide. All right, so this is a part, this is of course not the whole ontology. This is just a part of the ontology that we developed for climate change. And this is just a visualization of the ontology that we developed. So it becomes it becomes much easier for us to examine the patterns, just discover, just interpret classes, and to just the visualizing an ontology just enables us to understand the concept in a much better way, and also to discover if there are any hidden or if there are any patterns. Yeah, next slide. All right, so next is ontology evaluation. Of course, the ontology that we developed has been evaluated both qualitatively and quantitatively. So evaluation is a necessary process to enhance the ontology by obtaining feedback. So yeah, so we obtained feedback from over 80 users participated in the evaluation process. And the ontology that we developed is both evaluated quantitatively and qualitatively. And in this paper, a semiotics-based data approach has been used to estimate the ontology qualitatively. And ontology can be quantitatively assessed. Like, yeah, the ontology is here in our paper. The ontology is qualitatively estimated based on the semiotic-based data approach, while it is quantitatively assessed by analyzing the number of subclasses, leaf classes, attributes, reuse ratio, and reference ratio. Yes, next please. Next slide. All right, so upon evaluation, the reference ratio and the reuse ratio, during the evaluation, the reference ratio and the reuse ratio are calculated based on using those formulas that are illustrated here in those figures. The first reference ratio is calculated. Reference ratio, how it is calculated, is illustrated in the first figure. And the figure 2 depicts how reuse ratio is calculated, and figure 3 depicts how the reusability rate is calculated. So reusability rate is nothing but it's just a percentage of reuse ratio, and reuse ratio is calculated by the formula it's just calculated by number of classes divided by total number of subclasses divided by total number of classes, while reference ratio is calculated as shown in the figure 1, that is number of reference elements upon total number of elements. So the reference ratio that we obtained is 0, which means the ontology that we developed for climate change is the very first of its kind, and it has got no reference from any other existing ontologies. And the reuse ratio achieved is 0.95. Of course, that's great, right? And the reusability rate is 95%, and the depth of inheritance of the proposed climate change ontology is 5. So these reference ratio and reuse ratio, the depth of inheritance, clearly validates that this ontology can be used for any intended purposes. Next slide, please. All right, so this graph this graph actually compares the ontology evaluation based on various parameters that are used in semiotic approach. Semiotic approach. So the various parameters that we consider during the evaluation are accuracy, clarity, comprehensiveness, consistency, interpretability, lawfulness, relevance, and richness. As you can see, the blue bar represents the climate change ontology. It has a better accuracy, clarity, or any other measure comparing. Yeah, it has a better accuracy, clarity, comprehensiveness, interpretability, and lawfulness, and almost a very good equal richness to that of red. So it's yeah. So the results that we obtained is really great, and it actually validates our proposed ontology. Yes, it just validates the efficiency of a proposed ontology. Next slide, please. Yeah, so quantitative ontology properties, the climate change. Yeah, so the evaluation is done based on with the participation of 80, it has 80 parties, actually 80 persons or 80 people participated in the evaluation process, and the evaluation is done based on some metrics such as accuracy, clarity, comprehensiveness, consistency, interpretability, lawfulness, relevance, and richness. And the table to the right, the table that's in the right of the slide, it illustrates some, it just highlights some data about the ontology that we developed. And yeah, so based on that, you can see the total number of classes is 100, where the number of subclasses is 95, and the number of attributes is 33, the number of leaf classes is 50, and the reuse ratio achieved is 0.95 with reference 0.1, which again makes it the first kind. Yeah, please, next slide. All right, so here we go. The ontology or knowledge-based climate change developed is first of its kind. It's very evident as the reference ratio that we obtained is 0, and an in-depth study on climate change has been done to define and relate the concepts. The ontology has been modeled by considering the complicated phenomenon in climate change. A geological and the social technical aspect are considered for ontology modeling. Subsequently, the ontology is modeled in ontology web language, that's OWL. And Web Prodigy is a software that's used for visualization of the model conceptual ontology for climate change. And furthermore, the ontology is evaluated both quantitatively and qualitatively. The qualitative evaluation is done based on the semiotic approach. And the result of the evaluation implies or validates that the ontology can be used for any intended purposes. So finally, the reuse ratio of 0.95 has been achieved with a reference ratio of 0, which makes the proposed climate ontology effective and the first of its kind. Next. All right, so these are all the references that we consider, like that we have. These are the reference are illustrated here. The reference that we consider for our paper are illustrated here. Thank you very much. Thank you. All right. In case of any queries, feel free to contact us. We have our email IDs here. It's me, Deepak Surya. We have Mr. Gerard Deepak there. So in case of any queries, you can feel free to contact us, and we will get back to you as early as possible. Thank you.